Okay, so we're going to learn a little bit more about the nuts and bolts of C++. Now, some languages, this is not a problem, and it's because they're kind of more interpreted. They're not built for speed. They can figure things out on the fly. C++, for a lot of reasons, especially the size of the programs that we might write, like we're talking 4 million line programs, we really want a very locked down system. So this idea about library design and preprocessors and this weird thing called include guards are kind of like the plumbing underneath what we do at a very large company. We might never run into it, but when we go out to do bigger and bigger things, and especially in four-year colleges where you go follow computer science and they teach you C++, they don't really take you into the details of this. They just maybe kind of throw it at you. I myself did not really understand what was going on for quite a few years because I just sort of took what they said and ran with it. So I'm going to try to give you a little more information underneath. But if you don't get it all, don't worry. You can kind of get by. But if you're looking for a little more secret sauce, this is kind of going to give you that in this lecture. So more and more .h and .cpp files. That's going to challenge a little bit of our kind of submission process. But we're going to do a lab today where we separate the .h and the .cpps from each other, and where you're going to kind of be writing these things totally from scratch. So that's good practice. It's really simple examples of classes, but you'll see it's really easy to make mistakes. Also, later in the week, we will enter into the world of templated functions, or for those of you who have ever worked in Java, those might be called generics. They're pretty cool. We'll talk about that on Thursday. And that will be an optional lab, and I will have an update on our risk game collaboration. So apologies, we just chucked that at you and didn't really talk about that again, but I've been trying to catch up in the background so that it's not completely disorganized. So we'll have a little bit more for you in that lecture as well, and we'll try to kind of have another activity for you, but maybe we'll like leave it open so it's not like a Friday deadline kind of thing. Won't affect us, but I know, people like me forget that we have a holiday. So Monday is President's Day. So you will not obviously be having classes that day, but we do have our deadlines for the quiz 2 and the homework 2. So remember both of those things. I know you'll probably have a lot to do this weekend. So maybe jump on that a little bit early this week if you can. 3 quick slides on review. So remember that when we have an instance of something inside of a class as one of its data members, that thing takes up memory. So it literally takes up space inside of the instance of the car. It's not like floating outside and we kind of go find it via some pointer. It's actually physically taking up space like a box inside of a drawer, if you want, right? So there's a little bit of magic that goes on there, but that's kind of at a high level what's happening when we have a data type and then some variable. It's like int x or float x, engine E takes up space. And so that's what we tend to call composition of classes. We will begin to do a little bit more with this where we say, okay, I don't really want to put the engine inside of the car. I want it floating next to the car. So I'm going to hold on to a pointer and I'll just follow that pointer whenever I need to find the engine. This is kind of messier, but allows us to maybe share the engine with another car. That doesn't really happen in the real world, but it might make sense when we're doing stuff inside of a computer. And we will actually see that in one of our homework problems that are coming up. So, but we also have a little more responsibility in this model to delete. So we release the memory when we delete the car. If we delete the car on the right side, we got to also delete the engine and the wheels and the radio. Okay. On the other side, on the left, you delete the car and everything goes away with it. So there's some pro and con there, and we'll learn about those situations here as we kind of go forward. Other thing we said that is, I think, really cool, but I think a lot of people, including me in the beginning, were like, wait, why isn't this working? If I want to have an array of instances, I can have that. So think of it like our good old ice cube tray, but here the ice cubes are not integers or floats. They are entire copies of a wheel. But as you can see, I have no description of the constructor there. I'm not saying, well, the wheel has a certain number of miles on it. So in order to do that kind of thing, your wheel class must have a fully defaulted constructor. Either you've got all your defaults for the arguments specified, or you've got an individual standalone constructor that doesn't require arguments. Once you do that, you can now have this wonderful world of two-dimensional arrays or four-dimensional arrays, anything you want that has instances of a class in it. So that's kind of a handy thing to be able to do when you want to do that. Now, increasingly, we will start working with vectors, and we saw that a little bit last time. The disadvantage of vectors, of course, is if you know you're always going to have four wheels, it's a little, extra step with vectors to create those four wheels. Here, the constructor for the car is going to create the wheels for us right off the bat. We don't have to worry about doing that if we don't want to. Okay, so that's just it's a little old school, but it actually is a nice way to go. Here we see our empty wheel vector, right? Instances of wheels, but there's nothing there yet. So there's no constructor being called yet for the wheels. That happens right inside of our constructor. And this is just the .h for our constructor. So we'll have to go look at the CPP to see that. And we won't do that again because we did that last time. But there's two different approaches, and we'll keep reflecting on both approaches to kind of expand our understanding of how all these things kind of come together. Now, we will, as I mentioned, have a situation like this where we might be collecting pointers to wheel instances, not just instances of wheels. So just that little star right there says that what we're collecting there or pushing back into the vector is an address in memory, not an instance. So that's a whole different ball game altogether. And we talked about that a little bit as well. Okay, so lots of different possibilities. We think of ourselves as, creators or builders inside of this digital world. All of these are really fun tools that we get to choose from when we're starting to build exotic data structures. Okay. So good to come back and think about that stuff. Today, we are going to start talking about a couple more classes, strategies, or gotchas. One gotcha that kind of can throw you for a loop the first time you see it is, okay, let's see, I'm a person class, and I kind of have a best friend who's a person. What are the different ways in which I can build that in as a data member, okay? So we'll look at the pros and cons of trying to point to my best friend or myself versus having a copy of my best friend or myself, okay? And that'll kind of lead us into a broader discussion around library design. We'll talk about the idea of prototypes again and implementations, or .h files and .cpp files. So we want to say, actually I got that backwards. Declare is our .h file, sorry, and define is our CPP. Don't worry so much about that terminology. Once you kind of know the code, you'll know what you're doing. But in order to really do that, we need to understand a bit more about what these C preprocessor directives are. Anytime you see a pound sign, that means that before the compiler starts, there's this robot. It's like a giant copy-paste robot, and it is picking up files from your file system and copying and pasting them all over the place. It has nothing to do with C++. That robot does not understand C++. All it knows how to do is be a copy-paste monster. And so we see things like pound include. That is like a copy-paste directive. It's like, hey, go get that code over there, paste it exactly right here. That's the copy-paste directive. We will also explore today some others, pound defined, pound if def, pound end if. You can do some pretty crazy things with these things, and people certainly do. We'll just explore a couple of them, particularly related to how we have to work in larger teams. So that will involve our if def or if not defined and our define directive. And we'll talk about what those things mean today. Okay, so whenever you compile a C++ program, typically that compiler knows how to go call the preprocessor. So if you just throw some pound defines in there, typically you'll be in pretty good shape. But not all compilers support that, but they are pretty common. We'll also look at one that is sometimes frowned upon, but I gotta say I really like it because you'll see when we talk about it, it's simpler and an alternative to this if-def here. It's called pragma once. And so we'll just show you how you can use that, and you can choose either path. Probably this one is more, if you go work at Google, they're going to tell you to use that one there. But in class, sometimes this one is just better for our sanity. But you can kind of explore both of those approaches. Okay. So take me to your include.h file. That's kind of what's going on inside of our CPP file. .h files never get compiled. They just get shoved into our .cpp files, right? And then the .h file just sits there on our file system and does nothing, right? Because we've already grabbed its contents, okay? So we'll come back to that. Let's do a real quick side trip to talk about this topic of self-referencing, which I think is really interesting. So if I wanted to do this, seems like a natural thing. I'm a person and I have a best friend who's a person, so why not create a data member that is a person, right? That seems like that should be okay. But when you try to do that very simple thing, what you really get is a recursively defined person. That includes a person, which includes a person, which includes a person. And the compiler just blows up and says, I can't do that for you. So you're stopped dead in your tracks and you think, how am I going to do that? So you think, okay, well, maybe I'll do this. We'll create a vector of best friends. And I know it's not going to put any friends in there until I put a friend. That's an empty vector with no best friends in it. So I can sneak around, come back later and add some instances. So that actually could be one way to do it, right? So the problem with that, of course, is if somebody changes their name, we only have a copy of our best friend in our vector, right? And so copies, of course, don't update themselves across all memory. So there's some problems with that particular approach as well. So kind of a little dangerous. This one is kind of where we end up going eventually. This is why pointers ultimately are unescapable. It's like, well, kind of I want to point to my best friend so that if my best friend changes their name, then all I do is go check, go follow the pointer to them and I see, oh, you've changed your name, right? And I don't have a bad copy of my best friend. So pointers allow us to do that, and collecting pointers inside of vectors or arrays, but more modernly vectors, is a really, really great way to build powerful data structures. So if we think of our vector as an accordion that gets bigger and smaller, starts out small, gets bigger, we're filling it with pointers, not instances of some other class. And that's a pretty good way to go. Now we could simplify and say, well, I only ever have one best friend, so that will be my pointer, and we could just do away with the whole vector altogether. Okay? But these are, this spread of possible approaches is important for us all to kind of understand the trade-offs. And probably we do something like this, because even if we were allowed to only have one best friend, who knows, maybe your boss is going to come back later and go, hey, we've decided we're upgrading and we're going to have lots of best friends. So now you just got to add more best friends to that vector instead of changing your whole data structure. Okay. So we'll do a quick tour through this. You can kind of see what's going on here. But here's kind of the, recursively defined person inside of a person inside of a person. Can't do it because the compiler is going to just freak out, try to build that infinitely. And it's an interesting error to see, but we won't kind of dwell on that. Okay. So that one's generally not allowed. Not a good idea. Vector of instances, perfectly fine, but let's look at the code just so we get familiar with what's going on. We have Bill, and Bill's name is here, and he's going to have a best friend, and then we have Ted. So we're going to say Ted pushback Bill, right? So Bill is an instance, let's say, right, that has the name Bill, and Ted is an instance that has the name Ted. When I push back anything, it's a copy, okay? So you might say, well, wait, I just put Bill in there. Well, Bill gets instantly copied as a byproduct of the pushback method. So it's kind of a cloning machine. Anything you put between those parentheses gets copied. And now these two things are no longer linked. So of course, now what we have is Ted over here has a copy. So this is the copy that's inside of this vector, and it's Bill. But if we change the name of Bill by saying Bill.setName Will, right? Now this one over here on the left is Will, but we got a copy in Ted's best friend. So they're not linked. It's not a good situation. And generally, we wouldn't really build something like this if we wanted to support that kind of updating. Okay. So you can imagine in Facebook with all of these references to friends, those pretty much need to be pointers, as you can probably guess. I'm not keeping a copy probably of people. And we could debate what the meaning of a pointer is, right? But that's essentially what's probably going on there. Now here we're saying Ted, best friend, square bracket 0. So best friend is a vector. So we should be able to go to the 0th thing and say, well, if your name is equal to Bill, do something, right? So we're checking the 0th friend to see if it's Bill. And of course, we should see that it actually is, right? Because that's what it was when we actually created that thing, okay? So good to be aware of when the copies happen. Good to be aware, again, that we're using a dot here because we're not having a vector of pointers in that case, okay? So that's kind of our second example, moving in the direction of getting better, right? But has some flaws. So here's our ideal situation. So now we're saying, well, I'm going to point to you. So I'm going to push back a address of you, the instance. So if this is Bill, the instance, when I say push back, I need a pointer to a person. So ampersand Bill gets the address of a thing, right? So that says go get the address of Bill and push that back. So we are still copying, but we're copying an address. So if I tell you I live at 1313 Mockingbird Lane and you make a copy of that, both people are going to end up at the same address, right? So copies of addresses are kind of okay. Copies of instances, maybe not so much, right? So now we can say I've got a pointer pointing over there and I can come change that name. And of course, following up now, we will follow up with an arrow, right? Best friend 0 is the address that we just pushed back, right? And then inside of that location, we find a name, okay? So now I can compare and say, are you equal to Will? And the answer there should be true. Yes, because we did change that name to Will. So this is really probably where all of our more advanced data structures should be, is kind of keeping instances separate and, linking them together. Now, one example could be our molecule example where maybe I put an atom of hydrogen in my molecule, and then I want to change that to an isotope. I'm not a chemistry person, but I think if I muck around with hydrogen, I can make it some kind of a weird little isotope, right? So in that case, maybe I want a copy of hydrogen because I don't want to change all other molecules to be using isotopes, right? So we really got to think about the situation and think whether sharing that instance is the best idea, okay? So in this case, I think sharing is probably going to be best for us, okay? So good to just be aware of how we followed that syntax around, okay? Let's see, best pointers to best friends. So this is really the simplified version, right? Much, much more simplified. So I'm saying Ted.bestFriend equals the address of Bill. So I'm literally doing that, okay? So instead of pushing that address back into an array, I'm storing this Bill's address in this data member, which happens to be a pointer, okay? So many of us might have this stuff down cold, but it takes a little practice for the rest of us coming up to speed there. So those things hopefully anchor your understanding of pointers a little bit and the different approaches that we can make, okay? I think that is all I have to say about that one, okay? So if you want to do this one, right, and you can do this with either regular online compiler pro or the Replit, I would suggest coming back and doing that. I won't dive into that now because I think I did a pretty thorough kind of description over the top of that. But you should be able to do this, and don't assume that it's, slam dunk. Most of us, including me, trip over something along the way, okay? So maybe come back to that, see if you can fill that thing out and get that thing working, okay? Just good reinforcement for your using of .h and .cpp as well as pointers. So here's our just simple best friend .h file, right? So no curly braces here in the .h file, just our prototypes, okay? And our pointer to a person there, right? And passing in a pointer to a person. So got to use the ampersand on an instance in order to turn that thing into a pointer to a person, okay? So thus the star on that argument BF, okay? And then set BF is the same. Okay, so there's our null pointer, right? Notice that it's probably a good idea not to assume too much in your constructor. Go ahead and set that thing to null until somebody comes along and adds a best friend, okay? And notice this is a copy too. I'm taking your address and I'm storing it in my data member, okay? This is the argument. I created a copy. It's like saying I get a copy of x equals 5. Well, the thing I'm copying is a 5. No big deal. We've done that a million times, right? So that's all I'm really doing is just doing it with an address, location, and memory, okay? And because now best friend is a pointer, the get BF name has to use our little arrow there, okay? So we're saying, oh, I will follow my best friend's pointer and call their method to get their name, all right? So just want to make sure everybody's tracking on that stuff. Kind of almost got to close your eyes and imagine it. And so here is our, finally all of our code in main, okay? So all that should hang together for you. Okay, so that's kind of just a little bit of a tour around the bases for pointers and instances. Let's talk a little bit about, well, not a little bit, let's talk mostly about library design. And I really don't know what to call this. It's really .h's and .cpp's is what it really is. So I'm going to give you the really, really, really short answer on this one to start. So if I have a .h file and I want to go work for Google, this is what I'm going to do. If my .h file is called bolt.h, I'm going to use a preprocessor directive and say, hey, if I have not defined a variable that looks a lot like this file name, right? I just made up, it's like a variable name in the preprocessor. If I have not defined that already, go ahead and define it. So the robot preprocessor says, yeah, never heard of that before. So, okay, let's make it. Okay, now that exists. And now we have all of our normal code that goes inside of our .h. Notice that the end if down here goes with the if not defined, okay? So what we're essentially doing, and I'll explain why in a bit, we're saying, hey, if this is the first time, robot, you've opened this .h file, go ahead and pull it into whatever you're building right now. If you've seen it already, then you would have recognized that this variable existed because you, Mr. Robot, would have created it. So if somebody tries to include bolt.h twice in the same CPP file, the robot's going to go, no, that is defined, so I'm not going to follow your instructions because this is actually already defined. So it's just going to not do anything. And so this is the guarding part. What we're guarding against is preventing the same .h file from being pulled into a CPP file more than one time, okay? And you might think, I'm a good clean coder. I can avoid that. I don't really need those things. But as we'll see here shortly, it gets incredibly hard very quickly to prevent that problem from happening. So when I went to school, they just said, just do it. And they really didn't explain why. And I was pretty mystified for a lot of years. And I slowly started mucking around with those little include things and figured out like, oh yeah, and now I get it. But it really is the rule, right? So if you just follow this rule and you don't understand anything else about the rest of this lecture, you're going to be okay. So at that point, you could say the end, right? No more lecture, right? But I would like to dig a little deeper, right? So, but if you memorize that slide or that strategy, just that right there for every .h, you're going to be well past half the battle, okay? The rest of this is about a deeper level of understanding that will help you unwind some problems. So I kind of refer to it as define once, declare many. We can declare a .h file in a lot of separate .cpp files, but we really only want to have one CPP file that describes a particular class. Okay, and I'll show you what I mean in some diagrams. So think of the declaring as .h files and the defining as .cpp files. Okay. So when we compile a program, all of our CPP files get turned into little zeros and ones, and then they get glued together, okay? So the gluing together part has to ensure that only one time have we described exactly how our constructor for a class works, right? We don't want to have multiple CPP files kind of doing that, okay? So when we're just dealing with one CPP file, it's easy, right? It's like super easy. We put all of our classes in main and we compile them and we get a binary file with zeros and ones and life is good. It just works. It's simple. We don't have this mess. And that works in class, but if we go out into the real world, it's just not going to work that way, right? So what we really have is, even if it's just us, we might have a lot of CPP files that are dependent on each other. So if I just tried to put all these files in different CPP files, right, we're going to very quickly find out that the interrelationships between the CPP files lead to a bad situation where we have a lot of things represented twice, multiple definitions, maybe missing declarations. And the strategy with the include guards is the straightforward solution to that in C++. So Python doesn't really have it. Java doesn't really have it. So this, if you need a reason to hate C++, this would be the one reason. But there are things that it gives us, right? So I'll show you that here shortly, okay? So if we have lots of files, so say I have a 4 million line program like 3D Studio Max or Photoshop or Chrome or whatever, and it takes, I'm going to exaggerate, but let's say it takes 2 hours to compile, or even if it takes 20 minutes to compile, or let's say 10 minutes to compile. Imagine hitting the run button and waiting 10 minutes to see your results. That not only gets annoying, it prevents you from getting your job done. So what we want to be able to do is change a very small part of the code and only compile the part that we changed. And then the other almost 4 million lines has already been compiled and glued together, and we're just going to update one little piece of it, okay? So that is called incremental compilation, and it lets us do little tiny changes and not pay a really big cost when we get out into the big world. So that is one really big advantage of this kind of approach to C++, okay? The other thing it lets us do, of course, and we'll try to help you realize this with our risk game that we're doing, is we can work in separate groups. If we all agree on our .h files, we can all just sort of take off and start prototyping our other classes. So that's why those .h files become so crucial to get right early in the process, because we don't want to change them and break everybody else's code later on, okay? And it also means that we can kind of go back in and change the guts of our implementations without breaking everybody else's code. So one of you groups of the teams can say, well, I'm not going to change the .h, but we thought of a totally cool way to store our data. And since everybody's using getters and setters, then it really shouldn't hurt anybody, because that's how they should be using our code. So encapsulation allows us to make modifications while everybody else is still using our interface, okay? So there are really good reasons for this. The problems, of course, we got a sense of that already. Lots of files, lots of things to keep track of, and we got to do these include guards so that we don't get multiple declarations in a single CPP file, okay? And we'll show you how to do that, okay? Now, what are translation units? If you go out and you read about this problem, you're going to hear people talking about translation units. They're just CPP files that have been all dressed up. They're ready to go. And we'll show you a little picture of that. So our CPP file has .includes in it. But when we run it through the preprocessor, we get that big copy paste robot pulling in our .h's and filling out the CPP file. So we kind of call that our translation unit. It's ready for compilation. There's no more pound includes inside of it. It's got all of the pound includes pulled in and processed. So that is a building block for a much, much larger, potentially larger final executable. In a simple world, that's our main.cpp, and maybe it's just like a walk in the park. But if it's a 4 million line program, there's a whole lot of other stuff that's sitting out there, okay? But the key is there's going to be one declaration of a prototype per translation unit, not lots of them, okay? And you're probably saying, I can avoid that problem, but I'll show you why that is so hard to avoid, okay? So let's take a look at a not even very complicated situation. I'm going to get rid of this here altogether. So here I have my main file where I want to create an instance of an A class. So I'm going to at least have to include the .h in the main file because the compiler won't know what A is as a class. But I also have an A.cpp file that needs to include that, right? And the main wants to include B, etc. And we'll see this over and over. The permutations of inclusions start getting crazy, and it can very easily result in multiple declarations, right? So that is kind of the problem. All these include files, this is including that, right? And the preprocessor is going to end up creating multiple copies unintentionally, right? We only really want one in each of those, okay? So I guess my picture here is showing my include guards in yellow. So what I'm really showing here is the happy answer, right? Our include guards are all working. If there's a yellow around the box, that means I put an include guard around it so it doesn't get double included. And so in this situation, we have a happy ending, right? That thing compiles, and it creates what we call object files, right? These are zeros and ones, and the linker is this silent partner that does the last step. So if I change this file here, it's going to recompile that, redo that, and then the linker will glue them all together, but it didn't have to go back and do all these things, okay? So this is one of the many advantages of kind of coming up with this crazy system is we can just have little changes and then glue the parts together. So you might see linker errors in your file when you try to run it. And you probably always wonder, well, what is that thing? It says linker, can't find definition for blah, blah, blah. Well, that's the last step where it's gluing everything together. And it's looking around and said, hey, somebody promised me they were going to write a definition for that A.h, but you lied, you never did, or maybe you misspelled it, right? So the linker is the one that's shouting at you saying, yeah, I've looked everywhere and I cannot find an A.cpp file, or maybe there's a typo, right? So when you see linker, you know you're almost there. You're really close to the final process, okay? So that's really the big picture, right? And it's complicated, but it allows us to do so much, okay? So let's dig in a little bit on that preprocessor, just some of the directives that are there, right? So first off, if we want to remember that it happens before any compilation happens. So a lot of people are surprised by this. You have to imagine that you hire a bunch of painters, they come in, they paint your room white, and then you begin, okay? So the preprocessor can do really crazy magical things. In fact, you could use it for writing your essay or something, right? It doesn't have to be used for C++ if you don't want to. But it does literally change your code by copying and pasting other files, okay? And other little changes that we'll look into. Does not understand C++ at all. So you could have it change the word bananas into square root. So you could start writing C++ code with the word bananas in it, but then tell the preprocessor to replace bananas with the square root function. And it would work just fine. And no one would be the wiser. And it would look like bananas was an actual square root function. So there are a lot of ways that we can use this, not just the way we're focusing on today. But predominantly, we're just pulling in these .h files with a little copy paste action. And really, that file is getting really big. So when I say pound include vector, my CPP file just got really big, my translation unit, because the vector library is pretty big. We just never actually see it. So that one line, pound include vectors, like boop, there's a massive amount of code at the top of our file now, okay? So that's something many of us will never actually see, that file getting bigger, okay, before it gets converted into our zeros and ones, okay? So here is the sum total of all preprocessor things that we'll really care about. Include, define. It's creating a variable for the preprocessor, right? It's not for C++. It's not a variable in that sense. It's just like a little flag. It's like, hey, here's a flag for you. I can undefine it later on if I want to. I can test whether it's defined, and we got a little glimpse of that. And I can do kind of logical things. I could say, hey, if we're compiling for an Xbox, we can make it go faster with the following code, right? Or if I'm compiling for a PlayStation or a mobile phone, that's an old version, it's a different screen size, so do this. So if defing, they call it if defing or ifs, is a very common but sometimes not appreciated way of dealing with hardware specific issues on different platforms, right? And so you can go crazy with all this stuff. So we're going to just show you a couple of these and that's it, right? So let's look at the include directive. So we could just say, we do this all the time, right? This means, hey, go look in the system location for vector or string or whatever. We don't know where that is. It's on our computer. Or in the case of Program IZ and Replit, it's on their computer somewhere. So we can just call it up. But if I want to copy paste anything, you can certainly do that. You could say copy paste my main.cpp and put a copy of main.cpp inside of your main.cpp file. That would be crazy. In fact, that would be circular and it would probably crash the preprocessor. But there's nothing magical about the file that we put in there. So if I said include foo.xyz and bar.xyz, and they literally had that C++ code in there, that would probably work, right? So if the code that got put in there made sense to the compiler, who cares, right? It's just a giant copy paste, okay? And then the preprocessor comes along and produces this. And in this case, that's perfectly fine. So we could use the include to pull in actual CPP definitions, but it's not a good idea. We really only want to pull in .h files, and we'll see why that is. But the include is nothing more than a giant copy paste machine, okay? And when we're done, notice there's no pound includes. So a pound include vector or a pound include IO stream would be gone, and it would be replaced with all of the code that was a part of that if we could see inside of our translation unit, okay? So that's a little bit about what's going on. So let's just go look at this and see if we can, I forgot to rewrite this one. So I think I'm not going to dive into this, but trust me, we got a lot of material to cover, so it's not the end of the world. So this one I didn't convert. But basically, you can get away with it, right? So this is what we just saw. If I want to pull in some crazy code here, I can do that. And then the whole thing is going to just run, right? But it only is going to run if that code that ends up makes sense in a top-down fashion, okay? So that's what our preprocessor is doing for us. So we get something like that, okay? So we do not normally do this, and we will not normally do this. I just want to show you that the preprocessor is kind of a dumb beast as compared to our compiler, okay? So these are kind of our main points, something I really didn't understand for quite a while, okay? It was just sort of this mysterious thing, okay? So what we're going to do then is look into this strange thing called include guards. But again, if you just memorize that previous page, you don't have to worry too much about understanding this. But let's take a look at how this stuff works. So on a basic level, if I define debug, that's like a flag that has a big word debug on it. So if I include this file inside of some CPP file, the robot that's doing the copy pasting will remember that debug thing, okay? And then we'll do some stuff, okay? And down here I can say, and this doesn't really make sense, but I can say, well, if this is defined, then go ahead and do some more stuff, okay? But if I come back later and I say, okay, I really don't want that debug output in my game or my homework assignment, I can simply throw away that thing right there. I can say, well, I'll get rid of that and leave this code in place. So the preprocessor is going to strip out all of your actual debug code, leaving you only with high performance code left. So very often what we see out in the real world is people will say, okay, put your debug, everybody, inside of a pound if def called debug. And when we want to run debugs, we'll put a variable up top for the preprocessor. And when we're ready to ship the code, we'll take that out. And you don't have to go changing all this other code, okay? The preprocessor will change it for us. So it's kind of like having a step before the compiler that allows us to flip some big switches by having these little variables up top. So it literally, and I've seen this code, if def Xbox, do some things, end if def PlayStation, do some things, end if, okay? And then when it comes time to build a game or an application, you actually decide which of these things you want up there, okay? That's one of the things we can do with our define and if defined and end if kind of semantics for our preprocessor, okay? And of course, we can come back. This is what I was just saying. I could just either take it out altogether, or I could say, well, I've decided I want to undefine that. So I can say, take that thing away in case somebody else had already did it, okay? So we're taking that thing out. So we won't be doing any of this really in class, but this certainly is one of the very important things that happens inside out in the real world. And the compiler, this is what the compiler sees. It just doesn't even see that stuff in the middle because the preprocessor robot tears that thing out, right? And it also tears out that stuff too. So what we're sending to the compiler is smaller. It's not got all that junk in it that we don't want in there. And so our executable code ends up being smaller too, okay? So it actually does have a positive effect. Basically, our PlayStation code doesn't have any Xbox code in it, right? Sort of filling out the memory, right? Which we don't want, okay? So again, I'm just going to fly over the top of this one. I don't know how I missed these. I meant to convert them for you, but I'll show you the code and you're welcome to kind of copy paste it into a program IZ situation. But it's really what we just talked about is like undefining that flag and rerunning that thing and seeing that you get that result. Okay, you won't get the message. Okay. So now let's talk about if not defined. And this is where we're getting down to our include guards, okay? So if something is not defined, right? If there's a variable, we just sort of pulled it out of thin air and said, hey, if you've never seen the variable unique before, then go ahead and define it, right? So notice I have this kind of defined, sorry, this is there, right? You're back up again. So this is my start and end. If I have not seen this before, then go ahead and make it, and then we'll print this, but next time somebody tries to include this file, maybe a second time, it's not going to do that. It's going to say, whoa, hold on, we already did that. So I'm only ever going to print this one time. That's what an include guard is doing for us. If somebody tries accidentally or intentionally to include this file twice in the same CPP, it guards us from accidentally doing this twice, okay? Which is really the capability we're looking for here, okay? So in this case, I just put a little message in there, but you will be putting your entire class.h file inside of there, okay? And so this is what we call include guards. And it just works even if we can't visualize the whole process, okay? So we only put them in our .h's. We don't put them in our .cpps. And if we follow that, it works great. Now, if you're worried about, well, what do I call this variable? And what if I have a typo and I misspell them and they're not the same? Yeah, that's a problem. So there's this other approach where we just say pragma once. So what we're telling the preprocessor is, you get it. Just don't include this file more than once, right? Keep track yourself. I don't want to have to make a lot of messy code in my .h file. And that works too. So in this class, you're more than welcome to use the Pragma once. And a lot of places support it out there, but the really hardcore places like Facebook, I'm sure, and Google and the bigger companies will probably frown on you and say, we don't do that here. We use our include guards. Okay. But this will, help you retain your sanity, type a little bit less. Okay. Has the same results. Okay. Um, so yeah, unless you have a really messy file system, yeah, but none of us are going to really encounter that out. But that's the reason why bigger companies don't like it. Okay. Okay, now someday we won't have to do any of this anymore. In 2020, seems like a long time ago, they defined something very similar to Java. It's just not making its way out into the world as fast as people would like. And it doesn't really work yet in the systems that we use unless we upgrade our compiler. And even then, it's very inconsistently implemented. So you would think by 2025, we would have had this thing sorted out. But this is why companies take a really long time to adopt more modern compilers, because it's kind of not really universally supported. So fortunately, we got to live a little bit longer with this stuff. Okay. Questions on that before we go on? The Pragma once, what a preprocessor is. Okay, you might see some quiz questions on that, so maybe burn a try early just to get a look at that, but I think you'll see they're not very complicated. Just kind of tests your understanding of what's going on there. Okay, so let's look at kind of when these things get created. So we've talked a lot about the .h and the .cpp. So we'll say this right here is declaring to the compiler, hey, we are eventually going to write this. And this is here's how it works, the guts of it. So I like to refer to that as declaring and defining, but you can just think of it as .h getting pulled into the .cpp, right? Via the pound include, okay? That's really what we're doing, okay? So if we don't use include guards, and this is really probably unnecessary, it's just sort of telling you what a mess it could be. What we end up getting through all of those inclusions is lots of copies, right? So bolt includes bolt.h, engine has to include bolt.h, engines.cpp includes engine, which includes bolt.h. And so we're accruing many, many copies of the bolt.h in our CPP eventually, right? All of these relationships result in many, many extra inclusions. And so without the include guards, we may not realize it, but we are stacking up duplicate definitions and the compiler hates that. So this little thing is the solution to that problem, okay? Just do either the Pragma and notice that we choose this convention, capital Bolt underscore capital H for the definition so that we kind of all know what to call it for that particular file. And, usually it's not a problem, okay? So if that thing is defined, not defined, we'll do it. Otherwise, we don't do it twice. And you can just do it this way. So much cleaner, okay? Okay, sorry for the long description, but that might help you, right? So now we can do crazy, crazy things. We can have all sorts of inclusions and not have to worry about it at all. We really only get one copy of everything. That's the magic of doing the include guard thing, okay? So, and again, my yellow boxes imply we have added our include guard to the .h's, right? Only the .h's, not the CPPs, okay? Only .h's. And you can see that we include the .h in a CPP, but we don't include a CPP in the .h. So I know my arrows are a little confusing, but that's implying that we're pulling something in that way, okay? So I think I covered all this stuff, but if you want to come back to this slide, anytime, and we'll see this in code, you refer by name to a class, you are going to need a .h file for that class, okay? So if we're in main and we say, give me an engine, we need an engine.h file, okay? If I'm in engine and I say, give me a bolt, then I need a bolt.h in the engine.h file, okay? So it goes in a lot of different directions and gets pretty crazy. We never include a CPP file. Never, 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 never. If you see yourself saying pound include, CPP, no, stop right there. That's going to cause you a world of problems, okay? And they're hard to clean up, okay? So here's, all of the different ways, sorry, that we would actually pull this stuff in together, okay? So that gets pretty crazy because car has an engine, engine has a bolt, main has a car has .h, right? So it goes in many, many different directions. And our lab today is going to kind of show us that. So let's look at this one. Let's jump into this briefly. We would need program IZ Pro for this replet, but we want to add a new bolt class to the entire project. So this kind of mimics what we're going to do for our lab today. So I'll get you started, but don't worry if you don't have access to program IZ Pro here. It's not the end of the world. So let me just show you. And is it going to log in or make me log in? Oh, I really don't want to have to do that. That's really annoying. Okay, I'm going to bail on that because I'm going to, like most of you, I don't have all my passwords memorized, but I will just take you through the solution files, okay? So first off, we got to create a .h and a .cpp for our bolt, okay? So like our risk project, that's pretty easy to do. And then you just fill out the basics. So here's my bolt.h, pragma once, okay, class, and then a prototype for my constructor with no arguments. Just a simple constructor. And then here's my engine. Notice that because I am mentioning the bolt word there, I have to include bolt.h in the engine.h file because the compiler does not understand what we're talking about unless we get that thing in there, okay? So one copy gets pulled in via my include. Here's the wheel. We have a bolt in the wheel file too. So that's the goal of this practice, is add a bolt to everything. So we're including the bolt.h there as well, right? And then our car has an engine and a wheel. So we got to have those .h files in there, okay? So that's crucial as well. And then let's check out the top level. So this is a little maybe icing on the cake here. So notice that I'm only including car.h. It's okay to include wheel and engine, whatever, like go crazy. Every .h you can possibly think of, feel free to throw it in there because our include guards are gonna protect us. But if you really think about it, car.h already includes those things directly or indirectly. So by just including car.h, if we know the connections to all of the other .h files, we can do that. But who can remember that stuff, right? So just put it all in there and it's going to be just fine. Your include guards will ensure that you don't get duplicates in there, okay? So when in doubt, include your .h files in your main.cpp, okay? But if it starts working, you're probably okay. You've probably somehow indirectly included those things already, okay? So let me give you another minute on that one for folks who are kind of knocking that one out. It's a little tedious because you got to create that file and then you got to, hook it up to everything, okay? But we'll be doing a lot of that in our risk game and also for sure in our lab today, okay? Okay, let's see about this next one. I think I got this one. Let's hope I got this one because I do like this one. So I like thinking about mechanical things and then seeing if I can come up with the code that simulates them in some way. So I don't know a lot about fixing bikes, but I know enough how to shift gears on my bikes. So this thing is called a cassette and it has a repetition of gears, right? And every gear has teeth. So we can think of each of those discs or gears that we're in as just an instance of a class, and each of those has a different number of teeth. And if I collect all those things together, they call that a cassette, right? So one way to actually do that and to kind of simulate an active bike is to have a vector of gear instances, right? We could call that gears, right? Gears is a bunch of gear instances in a vector. Notice they're not pointers, they're just instances. And then I have, what is my current gear? What gear am I in right now? Okay. So that's my cassette. And so I need a class for my gear and a class for my cassette. And I'm going to need some .h files and some includes, right? And I'm going to need some include guards. Okay. And so we should be able to shift gears, and possibly, use this as a basis for an actual bike if we wanted to really simulate all that stuff. But notice what we're doing here. We're saying gears in our constructor. If somebody wants to have 5, rings on the back there, or usually it's like 11 or 12 on a mountain bike, we're going to be pushing back an instance of the gear. Now, I'm just going to call the gear constructor directly. So that's the name of the constructor, and I have to tell it how many teeth it has. So every time I do a pushback, I am constructing a gear on the fly and just chucking it into the gear's vector, okay? Not a pointer, it's an actual instance of the class, okay? So remember, pushback is a copy monster. It just makes copies of things, okay? So whatever we put in there gets duplicated, okay? So we're going to do that a bunch of times, and then we just get our vector with all of our kind of things in there, okay? And so we can go in and switch gears, and we'll know how many teeth each of those has, okay? And I'm sure there's more than one way to do this. But let's try to do this one, all right? So see if you can kind of click into this one and develop your .h and your .cpp files for these two classes. And I'll put the solution up here to kind of help you out a bit. But give your gear a private teeth variable and give your cassette a current gear variable, okay? And then give your cassette a vector of gear instances, not gear pointers, but gear instances, okay? And we're going to need to separate these things out into the .h and the .cpp files. And I'll show you the code here because I know it's a lot. Use your include guards as well. So this is standard procedure for where we're going in this class, okay? So let me help you out with that, okay? And in the end, you should be able to create a cassette in main with a certain number of gears, okay? And I want to point out one thing, and we'll do this again, but notice this is my main code here. I'm saying, hey, create a cassette called C. The constructor needs to have a vector to initialize the gears, the teeth per gear. So what is that crazy set of curly braces there? That is a collection, it's a vector of integers that we're going to use to create the teeth, okay? So that's part of our constructor, okay? So let's start with the gear. Pretty simple, right? Pragma once, private teeth, public constructor. Defaults go in the gear.h, okay? So remember that for your lab today. So that's, if you don't give me the number of teeth, I will assume it's going to be 0, and we leave that in the gear.h, okay? No curly braces, because that's going to be over in our gear.cpp, okay? Now over to our gear.cpp, we include the gear.h. Notice we have our scope resolution modifier, gear : class, gear constructor, teeth, no defaults, right? And then we will just say, okay, I'll take that, right? I will take this temporary variable and store it in the teeth private data member, okay? No default arguments, okay? That's our gear. Cassette, a little trickier, but not much. We have to include our vector here, okay? And our gear, okay? And we're in the cassette.h. So this is a classic mistake I see. People also include the cassette.h, but we're in the cassette.h. So we don't want a circular inclusion here. So we're not in the CPP. We're just laying out our prototype, which is going to be a vector. Notice the std double colon, really annoying, but that's what we got to do. Current gear. And then this is the tricky bit. So defaults in the cassette.h. Here's our defaults, right? And this is saying, hey, if you don't give me a vector of integers, I'm going to create one on the fly, and our constructor will just receive 11, 18, and 12. So many of you will eventually need to understand and be comfortable with that idea there, okay? So if this is a vector of integers, that's what this gets turned into, okay? As a default, if somebody doesn't give me that argument, okay? Okay, so we're in the .h, right? So that's our cassette.h. Got our pragma once up there, nice and clean, okay? Okay, and notice this is also important. There's some nasty bugs. We want to put gear.h below vector, okay? So in general, put your kind of, commercial caliber include files up top, and then our stuff goes below that, okay? We'll come back to why that might save you some nasty bugs, but generally you're safe, but I would do that always, always, always to stay out of trouble, okay? And then our cassette.cpp, no defaults, right? And we're going to loop through the size of our vector, right? So here's all those teeth. We're going to loop through the size, tooth counts.size. And then we're going to push back a constructor with the number of gears coming from that vector right there, tooth count, square bracket I, okay? 3 teeth, then 12 teeth, and 18 teeth, whatever comes from that, okay? Putting a copy in there, and we're done with our for, and we're done with our constructor, okay? Now, this thing needs to have the vector also, the IO stream, if we're printing, and then we have to have our cassette.h, okay? And we have to have our gear.h. You might think, why? Well, because we use the word gear here, and the compiler doesn't know what that means unless we tell it what that means, okay? You can see we're slowly building up all of these references, which is a little tedious, and then do our main cassette and gear, right? We just create one of each, okay? And probably we don't need this, right? Probably because this has gear, we're already covered. But when in doubt, if you're using your include guards properly, it really doesn't matter. So just throw everything in there, okay? And this is me saying, this is the vector of integers for the teeth, and this is where we start out in gear 0, right, on our bike, okay? And you could combine, you could build an actual gearing mechanism with a front chain, back chain, figure out the velocity of all that stuff. You could go crazy with that, make a real bike with that if you really wanted to, okay? So that is that for the lecture. We'll jump into both the lab, and I'm going to give you a little hints on the homework. So if you can kind of hang until just another couple minutes here, we should get you out before 7 for folks who got to go. But I just want to show you these two things. So hang tight with me. Let's talk about our lab today. So you have a main.cpp file that has everything in it the old-fashioned way, like this, okay? So what we want you to do is break this thing apart and take it out of the main.cpp file and move it into their own respective .h and .cpp files, okay? So d.h, d.cpp, c.h, and c.cpp, etc. And of course, you'll notice that A has a B member, B has a C member, D has a D member, etc. Okay? And I've given you some default values. So I'll let you guys kind of decode that a little bit. But all we're doing in main is creating an A, and that should, like a Russian doll, it's going to just include all of those other things inside of other things. And it's going to exercise all of these kind of relationships. But you'll know pretty darn quick if you didn't get these right. But once you get these right, make sure you either delete or comment out this stuff in the main file, right? Because you're going to put them all over here in their separate files, right? So it's going to go into all of those separate files. So if you're getting a linker error, it's because you forgot to remove that stuff, okay? But if you get it right, well, first off, when you start, it should print that right there. It should just print DCBA, okay? Which is pretty funny because if you construct A, you're going to see it constructing from the bottom up. It's going to go all the way down to the Russian doll on the inside of the inside of the inside, make that one first, and then unwind. So there's a little bit of a surprise in this one about the order in which these composed, nested classes get constructed. They really come from the bottom up. Okay, so there's a little hint there. So you're going to need all of these files in your submitted solution, including your modified main.cpp. So ideally, I'd like to get 9 files from you for your lab today, so I don't have to go searching for them. If you are unable to get into Pro or VS Code or just otherwise upload these things separately, let me know. But ideally, I'd like to see these files from you. And you can either do it this way, right? Make sure you change this name to be whatever the .h file is you're in, right? Or you can do the pragma once, which is just easier to deal with. Okay. So that's an annoying little lab, but a good warm up for where we're going. Okay. Questions on that before I kind of do a quick flyover on homework 2? Okay. All right. Hang in there. Thanks for your patience. Okay. Little guidance. So just a reminder, you're asked to make 3 constructors, but it's okay if you want to combine them into one using defaults. Okay. But this is functionally what I need. I need to be able to call with no arguments, 1 argument, 2 arguments. Okay. So you can do it this way, right? Just break these things apart. Remember, in their out of class CPP files, you're going to have this class name and then the constructor, class name constructor, right? No outer curly braces in the CPP file, okay? Now, you might be a little confused by this. For those of you who can think way back to our elephant puzzle, where we used a vector to initialize a 2-dimensional thing row by row by row. That's what we're doing in tic-tac-toe. I'm going to give you the board in an initially 1-dimensional form, and your constructor is going to have to copy that in. I'll show you that here in just a second, but that's what I'm hinting at right here, okay? So here's how you do that, okay? Think of it as just sort of following along and copying from position 0 and then incrementing a counter, right? Go again, increment a counter, right? So every time you copy something, you increment a counter and put it into its location, okay? Might be a little bit of a head scratcher if you don't remember your elephant puzzle, but let me know if you have questions on that. We can sort that out, okay? So let me just pause on that for a moment. So you're going to need a double for loop to do this, right? Outer is rows, inner is columns, but you're going to be copying from a 1-dimensional location and incrementing a counter, okay? Enough said on that one. You can put all your constructors in one thing, but remember, again, your .h has the defaults, not your .cpp, right? So you can get away with something like this. Of course, you got to put your code in here, okay? The compiler errors on this are so confusing, so that's why I spend so much time on it. Here are your methods. Take turn, make a move, right? Try to put this token in this location, okay? If there's something there other than an empty thing, then somebody's cheating, right? And please note, 1 to 3, these are not 0-based values. So if you don't adhere to that, you will fail the unit tests, which are automated, okay? So just subtract 1 from R and subtract 1 from C right away, and you'll be okay, okay? Otherwise, you're probably going to crash, okay? Is when, return true if this character has won the game, okay? Could be an X, could be an O, okay? but make sure you check that character, okay? Is tie is a little trickier. Return true if the game is a tie, okay? So you'll have to maybe think about that a little bit. Print the game, right? Okay, double check. Happens all the time. And then we get into an argument where I say, well, I know, but the specification says 1 to 3, and so I need you to do the 1 to 3 range, okay? So please keep that in mind. That's really kind of part of the specification, even though like the programming language can't limit the range of legal values for R and C. I wish it could. There are some languages that do, but C++ doesn't let us put that in the prototype specification. It would be really cool if it would, okay? So please keep that in mind, okay? Now, is when. Remember, we got to check rows, columns, or diagonals, okay? So for this player, okay? So we're gonna need to think about that particular player. Did they win or not, okay? So if it's player X, we're gonna check for all rows, right? Do a loop, right? This can be a loop, right? We know we got 3 rows. See if you got something for a win for that row. And it's helpful if you print an appropriate message, right? Hey, on row 2, I got a win, right? X is the winner, okay? Or column 3, you know, Y is the winner, whatever that happens to be, okay? So I'll let you guys figure that one out. It's not too hard, especially if you've taken algorithms. That one's kind of almost a walk in the park, right? Now, if you want to do the bonus, it's kind of fun. See if you can figure out an early tie, okay? So enhance your is-tie function. If you ever played tic-tac-toe a lot, you know, oh, this game is going to be a tie, right? So see if you can apply some of that innate knowledge that you have to predict whether the game is a tie before the board is fully filled up, okay? And remember that X is always going to go first, okay? So you can kind of look at this and know, okay, given the number of things on the board, if X goes first, I know whose turn it is, so it's a tie, right? So you gotta sort of think that way, okay? So that's why it's not, you know, totally obvious, the bonus, okay? Now, the last thing I'll tell you, I'll let you guys get out of here. You might be interested to know, I've changed a little bit about how I'm doing the tests. If you rename this thing, take off the rename, the compiler is going to slurp it up as if it's part of your program. If you don't rename it, the compiler never sees it. So if you don't want to run automated tests, just leave it as .rename. If you do rename it, I'd say wait until you've tested your code a little bit, but take a look at this strategy. This is how most people do unit testing. So notice that I've got a class here called testMe, and it's got some stuff in the middle, but mostly it's got a giant constructor. That's where my testing happens. And you might think, well, that's just the class. How does the actual testing begin? Well, at the bottom of my testme.cpp file, I create an instance of myself, which automatically calls a constructor, and we are agreeing on a tic-tac-toe prototype. So I am going to call your functions using that exact prototype, okay? So if you shouldn't, but let's say you change your prototype to change the name of your functions, well, now my testme is going to fail because I wrote my testme against the specification we all agreed on. You know, obviously I agreed on it and made you guys agree on it. But so if you decide for some reason you want to change tic-tac-toe.h, that means you have to rewrite the testme, okay? But let's have a conversation about that if you want to do that. It's a great exercise to learn about unit testing, but it's not something you should have to do. But then when you run your program, it's going to create an instance of this first and run the test before it even gets here, right? So the last thing, my animations are out of order. So we agree on the prototype, we create an instance, constructor runs. If you pass, then your game will play because main goes last. That's the interesting thing about this. Just by linking in a CPP file, it's going to instantiate the class, call the constructor, and test everything before your main even executes, okay? So only if you rename this thing right here. Okay. And that's a really nice, clean strategy to keep the testing out of your way. So your main doesn't get all goofy with all my extra code in there. Okay. It's one way to actually manage the unit testing. Okay. So I'll leave you with that. And hopefully that gives you enough to start. You guys stay dry this week. I'll see you on Thursday, and I'll stick around, of course, for questions. Come back or just raise a hand. I'll come back. Okay. Thanks, everybody. See you on Thursday.